Hello everyone, my name is Maryaradhiya and today I will be presenting my final term project for the subject Computational Microelectronics. My topic for this project is to analyze the DC characteristic of a double gate MOSFET. So the contents for this project is as follows. First, the device information about the double gate MOSFET, followed by the nonlinear Poisson equation and drift diffusion model which will be used to perform the simulation, and finally the results for the DC simulation will be presented. So first let's go through the device parameter used in this presentation to perform the DC characteristic analysis of a double gate MOSFET. The figure shown here is a simple double gate silicon and silicon dioxide structure. The transistor is assumed to be doped by a large N+ electron density at the source and drain region and lowly doped by electron density N in between the source and drain region. Here I have also presented the parameters that will be used while performing the simulation. For example, the N+ region doping density and lowly dope N region doping density. Also, the total length of the material is 120 nanometer, where each region is equally divided into 40 nanometer. The oxide thickness is given as 0.5 nanometer and the silicon thickness is 2 nanometer. Next is a simple block diagram of how to proceed and the steps that will be used to perform the simulation. So first we find the initial guesses for the electron density and the potential phi. We have to choose a mixed boundary conditions for the potential. Then we need to solve the nonlinear 2D Poisson equation at equilibrium when there is no applied voltage. Here in the Poisson equation we can omit the p term, the whole term, as we are only considering the electrons for our double gate structure. Other parameters remains the same in the equation. Then in the next step we start from the equilibrium and apply a voltage at the contact. The whole coupled system is considered. We perform this by following the drift diffusion model, which involves the coupled system of Poisson and electron continuity solver. We will also be using a Newton-Raphson iteration method to perform this, and until it converges to a provided value, the loop continues. Then once it converges, we will calculate the total current, which is given by the electron current density equation plus the whole current density equation, but in our case we can omit the whole current density, so it's only equal to the electron current density. Next, I have provided the boundary conditions. Since here we have quite many contacts and with different interfaces in our double gate structure, we have few boundary conditions at different contacts. Like at drain, source and gate contact, the potential is fixed, which is why we have applied Dirichlet type boundary condition. The source voltage is kept to 0, hence no Vs term is present. Then for the top, bottom, right and left surfaces, being the insulating surface, we apply Newman boundary conditions. Also, in the nonlinear Poisson equation, we initially assume electron density N as the given expression, which is also dependent on the electrostatic potential at that point. And for the initial potential, we also have certain expression as shown here, which is denoted as phi naught. Next, we have nonlinear Poisson's equation and drift diffusion model. So in this presentation, we'll be using nonlinear Poisson's equation and drift diffusion model for the simulation of the double-gate MOS device. The drift diffusion model is widely used for simulation of carrier transport in semiconductor and is defined by the basic semiconductor equations, which will be shown ahead. Here I have provided the simple Poisson equation that will be used in our analysis. The Poisson equation is given in terms of hole density, electron density, and doping density N+. So if the device is N type, then N+ will be positive value. And in our case, we don't need to consider the hole density peak term again. So the calculating the electron density N is our main goal here, and we'll perform that later. But first, we assume the Poisson equation without the hole and electron density and discretize it to get the basic scale version in one dimension, which can also be done in two dimensions, in our case, by adding a y component. And then in order to calculate the electron density and we need to solve additional equations. So if we want to know the electron density, we have to solve additional equation for electron density by using the electron continuity equation. So now we need two different equations, one for Poisson and other for electron density, that is continuity equation. So these two equations will be our basis for our analysis. Here in the continuity equation, the flux Fn is related to the electron current density. Now we need to express Jn in terms of electron density N and potential phi. So here for electron density Jn, we introduce it as a sum of drift and diffusion term. After discretization, the current density equation, we have the residue component for electron continuity equation. In order to find the Jacobian matrix, we find the partial differential equations of the residue component at I with respect to the unknown variables like phi and n in two dimensions. So now we have two different equations and two different variables at each vertex. We can arrange these two values as given form and solve the matrix to find the potential and electron density. Moving on to the next implementation of the theory. First, the initial value calculation is done where the mass size for the phi and the electron are declared and the initial condition values are assigned. In the nonlinear Poisson solver using Newton's iteration method, the residue and the Jacobian matrix is constructed for phi as shown. Then we apply the bias damping loop where Vd, the drain voltage, is varied from 0 volt to 1 volt, and for the gate voltage as well is varied from 0 volt to 1 volt slowly. Then we construct the electron continuity equation for different interfaces for silicon and silicon dioxide interface and construct the residue and Jacobian matrix for electron density using the phi value which was calculated earlier. Also, the assignment of the boundary conditions to the residue and Jacobian matrix are done for phi and electron for various nodes like source and drain, drain silicon contact, top gate, bottom gate, left and the right boundary surfaces. Finally, the Poisson plus electron continuity equation matrix is formed and the terminal current is calculated, which is equal to the current density which was calculated multiplied by the area of the terminal node, and then we will plot this current with respect to the gate voltage that was varied, and also the electrostatic potential and electron density curve will be plotted according to the voltage variation. Moving on to the simulation results. So here I have plotted the potential electrostatic potential graph with respect to the variation in gate voltage from 0 volt to 1 volt. And further, the electron density graph has also been plotted, was calculated, and based on the electric potential obtained with respect to the gate voltage variation. So there are no electrons in the oxide region, and the silicon region closest to the center of the gate has the highest electron concentration value. Finally, the transfer characteristic curve of ID drain current versus the gate voltage, the variation of gate voltage has been plotted under the linear scale and analyzed with the implementation of drift diffusion model. So with this, I would like to conclude my today's presentation. Thank you.